Assalamualaikum and salam sejahtera. So let's continue our lecture by chapter 3. The topic is momentum and impulse. There are two subtopics here, which is 3.1 linear motion and 3.2 conservation of linear momentum. And the time suggested here is 0.5 hours or 30 minutes. Alright, so we just start by 3.1, which is under linear motion. So according to the learning outcome, students should be able to define momentum and impulse, which is J equals to F delta T, solve problem related to impulse and impulse momentum theorem, and lastly, use F against T graph to determine impulse. Okay, let's start by the definition of momentum and impulse. What is a momentum? Momentum is defined as the product of mass m and the velocity v. So the product of mass and velocity giving you momentum. Alright, so the equation is P equals to mv. So remember, velocity is under vector, and then the momentum also under vector. Then the direction of the momentum is same as the direction of the velocity. So momentum and velocity, they are directly proportional. When the velocity just directed to the right, of course the momentum also directed to the right. The SI unit of linear momentum is kilogram meter per second or Newton second. And then what does it mean by impulse? Impulse is defined as the product of force F and the time interval, which is delta T. So F multiplied by delta T giving you the impulse. So the symbol of impulse is J. Then the question is J equals to F delta T. Again, force is under vector, so that impulse also under vector, and again J and F, they are directly proportional, so that impulse is a vector quantity and its direction is same as the direction of the force on the object. Okay, so remember, they are directly proportional, so the direction of J and F still the same. For example, when the force just directed to the left, so that the impulse also directed to the left. Okay, and then the SI unit for impulse is Newton second or kilogram meter per second. What is the relationship between momentum and impulse? So let's continue by the next part, which is under impulse momentum theorem. Okay, what is that? Impulse momentum theorem states that the change in momentum of an object equals the impulse applied to it. Okay, the keyword is momentum and then impulse. So the change in momentum and impulse, they are equal to each other, or we may simplify it using this equation. J equals to F delta T equals to delta P. Alright, so remember, J representing impulse, impulse T equals to F delta T, and according to this theorem, the impulse T equals to the change in momentum, which is delta P. Okay, what do we get by this theorem is, the second equation getting now is Ft equals to m delta V. Alright, how do we get that? Let me show you. As we know, impulse is J. J equals to F delta T. Still equals to the change in momentum, which is delta P. So the change in momentum, which is delta P, equals to P final minus P P initial, where P final equals to mv, while P initials equals to mu. Based on this, we may simplify it to be m multiplied by v minus u, where v minus u representing the change in velocity, isn't it? We may simplify it to be m delta v. So still equals to f delta t. So this is the second equation getting from the impulse momentum theorem. And then what do we get from this equation actually? Alright, this theorem reveals some interesting relationship, such as the inverse relation between force and time. Okay, what does it mean? In this case, force and time, they are inversely proportional. Okay, for example, here we are discussing about F multiplied by T giving you m delta v. So in this case, the impulse depends on F and T, but they are inverse to each other. And for example, for the first case, in this case, small force exerted on the object now, then the times for the collision is longer, alright, giving you the change in momentum. So according to this situation, for any longer time, the impact is not so strong, okay, because the force is quite small, isn't it? Compared to the second situation, where greater force exerted on the object and the time for the collision is shorter. So according to the greater force here and shorter time for the collisions, we can see the impact here, which is stronger than the first example before, isn't it? Alright, so F and T here, they are inverse to each other. Smaller force, longer time. Okay, and then greater force, shorter time. So we can see the effect lah. So at shorter time, for the impact should be stronger. Okay, and then for any longer time, the force is smaller, then the impact is not so strong. Alright, so this is the ideas lah, can be explained by the impulse momentum theorem. Okay, let's continue by the second subtopic. The topic is conservation of linear momentum, and according to the learning outcome, students should be able to state the principle of conservation of linear momentum. So what is the principle? Second, apply the principle of conservation of momentum in elastic and inelastic collision in one dimension and two dimension collisions. So there are two different types of collision to be understood here. And lastly, differentiate elastic and inelastic collision. Okay, so let's start by the principle of conservation of linear momentum. What is that? The principle of conservation of linear momentum states that in an isolated or closed system, the total momentum of that system is constant, or when the net external force on a system is zero, the total momentum of that system is constant. Again, the keyword given here is constant. Means that the value still remain the same. It doesn't change between initial and final. What values is that? The total momentum. Alright, but there is a condition. The condition is for any closed system. What does it mean by closed system? Where there is no external force exerted on it, or the net external force equals to zero. Okay, so according to the principle of conservation of linear momentum, we obtain that total momentum of the system is constant. What does it mean? The total of initial momentum equals the total of final momentum or we may simplify it using this equation where sum of P initial equals to sum of P final. But remember, the condition is sum of F equals to 0, or we call it as a closed system. Alright, so remember, initial and final momentum, they are remain the same, still equal to each other. Okay, now let's discuss about the total momentum for 1D collisions. Remember, 1D representing one dimension means that all the motion or maybe all the forces now just exerted on one axis only, and normally just involving the x-axis. Okay, what do we have now? Let's say by having two different bodies, which is M1 and M2. These two objects is moving now with its own velocity. So initially, M1 is moving with U1 and M2 is moving with U2. These two objects just move to the right. Okay, after that, what happened? M1 and M2, they just collide to each other. Then, after that, what happened? These two objects moving separately lah. Okay, M1 is moving to the right by V1 and M2 still move to the right by V2. So in this case, the total momentum for initial is M1 U1, and for the second body is M2 U2. So giving you M1 U1 plus M2 U2. And after the collision, what happened now? These two objects still moving to the right, isn't it? So the speed of the first body now is V1 and the speed of the second body is V2. So the momentum of the first body is M1 and V1. Okay, and the momentum for the second body is M2 and V2. So according to the principle, the total of momentum, which is for the initial and final situation, still remain the same or still equal to each other. So that M1 U1 plus M2 U2, this is the total of momentum for the initial situation, which is equal to M1 V1 plus M2 V2, representing the total momentum for the final situation. Or by giving you the second example here. Alright, so there are two different bodies now, which is M1 and M2. M1 is moving to the right with the initial speed of U1, and M2 is moving to the left with the initial speed of U2. After that, what happened? These two objects just collide to each other and sticks together. Then they are moving to the right by the same speed, which is V. So in this case, initially, the total momentum that we have now is M1 and U1 for the first body, and M2 and U2 for the second body. And finally, after the collision, what happened? These two bodies just sticks together, so the mass become total now, which is M1 plus M2. They are moving together with the same speed, so that the total momentum is M1 plus M2 multiplied by the speed V, now giving you the final momentum. So it still obey the principle lah, where the total of momentum initial and final, they are equal to each other. Okay, how about the total momentum for two-dimensional collisions? Okay, normally we are discussing about a motion, or maybe all the forces now just exerted two different axes, which is the x-axis and y-axis. Alright, so normally for this case, we need to separate all the calculation to be on x and y separately. Okay, so please refer to the diagram. There are two bodies given now, which is M1 and M2. Alright, so M1 is moving to the right by U1. So this is the velocity lah of U1. while M2 just keeps static. So U2 equals to 0. It doesn't move. Alright. So initially, what do we have now for the momentum? Only M1 and U1. M2 U2 just equals to 0. Okay, leave it first. Okay, after collision, what happened? Okay, after the collision, these two objects still moving now, but in two different directions. So this is M1 moving now with the velocity of V1, and the second body, which is M2, now is moving with its own velocity, which is V2. Alright, so please refer to U1. U1 now is really on the x-axis, isn't it? So we don't have to resolve it. But according to V1 and V2, seems like we are talking about the combination of two different axes, which is x and y. So normally we need to resolve these two vectors to be on x component, also on y component. Alright, so V1 we need to resolve it to be V1x, also V1y. And then for V2, still the same, we just do the same thing. We need to resolve it to be V2x, also V2y. Okay, according to the principle of conservation of momentum before, okay, as we know, the total of momentum has sum of P initial equal to sum of P final, isn't it? And remember, momentum is under vector. So for any 2D collision, we need to separate this equation to be on the x-axis, also on the y-axis. How is it? Okay, now, please refer to the diagram again. Okay, initially, the motion now just be on the x component. U1 is really on the x component. But finally, after the collision, seems like V1 and V2 just in combination of x and y components, isn't it? So again, this is V1x and this is V2x. This is V2y and this is V1y. Alright, so according to the principle, sum of P initial equals to sum of P final. But now we just start by the x component first. Alright, so total of momentum initial and final equal to each other, but for the x-axis. Initial on x, final on x. Alright, so according to the diagram, initially, what do we have now? The momentum is M1 and U1. And U1 is really on the x component, isn't it? We take it as U1x. So this is the initial momentum of M1. And then for M2, the momentum is M2 and then U2, which is U2x lah. But according to the situation, it doesn't move, so U2x equals to 0, isn't it? Automatically, M2 U2x equals to 0. After the collision, what happened? Remember, we are discussing about the x-axis, so we just refer to the x component only. Alright, so this is M2 and this is V2x. So for the second body, the momentum is M2 V2x, M2 V2x. And for the first body, the mass is M1 and the velocity now is V1x. So M1 V1x representing the total momentum of the first body after the collision. So this is the total momentum before and after the collision for the x-axis. Okay, now let's turn to for the y-axis. What do we have here? For the y-axis, still the same. Total of momentum initial and final, they are equal to each other. So P initial on y equals to P final on y. Okay, so initially what do we have? Again, M1 and then U1, but remember it must be U1Y. Okay, that one is the total momentum of the first body, and then for the second body, the total momentum should be M2 and U2, but it must be U2Y. That one is the total momentum of the second body. After the collision, the total momentum of the first body is M1 and V1Y. M1, V1Y. And then for the second body, the total momentum is M2 and V2Y, giving you M2 and V2Y. Alright, according to the diagram, for before the collision, seems like everything just on X component, isn't it? So we don't have any velocity on Y component, so that M1 U1Y equals to 0. M2 U2Y also equals to 0. Okay, next, after the collision, what happened now? These two objects just move into different direction, which is V1Y and V2Y. Alright, V1Y just directed downward, V2Y just directed upward. Okay, so remember the velocity is under vector, so we need to check its direction. So in this case, V1Y should be negative and V2Y should be positive. Okay, for the substitution lah. Alright, so this is the main equation for the y-axis lah. Okay, M1 U1Y plus M2 U2Y equals to M1 V1Y plus M2 V2Y. Next, what is the condition or characteristic for elastic and inelastic collision? Okay, we just go for it one by one. So there are two different types of collision, which is elastic and inelastic. So the condition or characteristic for elastic collision is, the first one is the total momentum is conserved. What does it mean? Sum of P initial equals to sum of P final. At the same time, the total kinetic also conserved, which is total K initial equals to total K final. While for any inelastic collision, okay, the total momentum still conserved. Again, P initial equals to P final, the total one. And then for the kinetic energy is not conserved. Alright, so total kinetic energy is not conserved for any inelastic collision. Means that total of K initial is not equals to the total of K final. So normally we just use the condition of total kinetic energy to determine or to prove the type of collisions. Okay, because according to the momentum for both type of collision, the total momentum still conserved. Okay, all these characteristics can be simplified by using an equation. So what is the equation? Alright, so according to the total momentum equation before is, okay, if the object moves separately after the collision, the total momentum of initial equals to the total of momentum final. Okay, they are equal to each other, which is M1 U1 plus M2 U2 equals to M1 V1 plus M2 V2. But if the object just sticks together after the collision, remember the equation become different now, where initially they are separate, so still the same, M1 U1 and then M2 U2, but after the collision they just sticks together, so that the total mass now is M1 plus M2, isn't it? So the final momentum is M1 plus M2 multiplied by V. Okay, they are sticks together, so that the speed should be the same lah. Okay, and then the total kinetic energy. Okay, if the total kinetic energy is conserved, so total of kinetic energy initial equals to the total of kinetic energy final. So for the initial one, what do we have? Two bodies now, which is A and B. So kinetic energy of A is half ma UA squared. So this is the total kinetic energy of A before the collision, and this is the total kinetic energy of B before the collision, which is half mb UB squared. Okay, after the collisions, the kinetic energy now is half ma VA squared. So this is the total kinetic energy of A after the collisions, and again half mb VB squared, representing the total kinetic energy of B after the collisions. Okay, so this is the total kinetic energy before the collision, and this is the total kinetic energy after the collision. Okay, they are separate. Okay, the body is still separate after the collision. Next, if the total kinetic energy is not conserved, so total of K initial is not equals to the total of K final. So again, kinetic energy of A before the collision, kinetic energy of B before collision, we just total up the values, and it must be different lah. They are not equal to each other. So this is the total kinetic energy of A after the collision, and this is the total kinetic energy of B after the collision. So remember, the values here should be different, okay, because the kinetic energy is not conserved. Okay, there are some wrong assumption done by student. Okay, so we just focus on this. Okay, we call it as wrong statement, okay, by student. So according to our student before, they just assume that for any elastic collision, the collision is elastic because after the collision, the object moves separately. So according to this situation, we just assume that the collision is under elastic, while for inelastic collision, the collision is inelastic because after the collision, the object sticks or move together. Okay, it's not necessary to be like that. It's wrong. Actually, how do we know is it under elastic or inelastic collision? So we just refer to the principle of conservation of kinetic energy. Okay, because according to our discussion before, the total kinetic energy just conserved for any elastic collision only, while under inelastic collision, the total kinetic energy is not conserved. Okay, so the correct statement should be like this lah. Elastic collision, okay, the collision is elastic only when the total kinetic energy before collision equal to the total kinetic energy after the collision. So the keyword is before and after collision, the total kinetic energy equal to each other. Alright, and then the object moves separately after collision. Okay, so this is one of the condition for the elastic collision. And then for any inelastic collision, the collision is inelastic only when the total kinetic energy before collision not equal to the total kinetic energy after collision. Okay, after and before collision, the total kinetic energy are different or is not equal to each other. Then the total kinetic energy after collision normally lesser than the total kinetic energy before the collision. After collision should be lesser than before collision. Why? Because some of the energy already lost to environment. Okay, the energy converted to be as heat or maybe as the sound energy. The object moves separately after collision, we call it as inelastic collision. Or the object sticks together after collision, we call it as perfectly inelastic collision. So remember, under inelastic collision, there are two different situations where the object can move separately or they just sticks together. Okay, their name also different. Moving separately, we call it as inelastic collision, while moving together, we call it as perfectly inelastic collision. Remember that. Okay?